Okay, hopefully everyone can see and hear me. Apologies if you can hear the laptop fan over this. As usual, this is my pre-recording of a talk that I'm going to be giving at the first Metascience Symposium at Oslo New University College. That's being held on the 25th of June. Now, this is to give you a little bit of a preface to this. Obviously, I'm running through this as a practice run through, as I normally do, to check timings, etc. But also to allow me to share a link to this uploaded video so that anyone in attendance, if I have to go through things a little bit quickly or things aren't clear, then people can go back and go over it in their own time. So as usual, I've tried to cram quite a lot into a relatively short 20-minute talk. So the background to this and the Metascience conference, the focus of this talk is going to be, despite the title, quite a heavy philosophy of science talk, using the example of competing theories of energy expenditure, or total energy expenditure specifically, and how that is determined, and what the competing models imply, and how we test them, and so on. And in particular using evidence synthesis methods to do so. Now, this is actually a kind of adapted version of a talk that I am giving in a few weeks at a particular workshop where we will be getting together a lot of people who work on these topics and trying to kind of discuss and solve the mysteries of energy expenditure compensation, as the title of the workshop implies. And in that workshop, I will probably not cover the background to models of total energy expenditure and so on, or at least in not so much detail, because the attendees will be fully aware of that background, or at least they should be. And I will, but I will be going through, because I think part of the what I want to present to the people, both at the Metascience conference, who I think will have substantive interest in the ideas of theory riskiness and appraisal, particularly in the face of competing theories which have different kind of levels of riskiness. I think this is an important thing for those working in this specific substantive topic area to consider as well. Okay, so with that aside then, I'm going to start my timer, and I will crack on with the presentation. So I hope you enjoy. Okay, so the title of this talk then is Meta-analytic Approaches to Testing Models of Energy Expenditure, Model Riskiness, and the Need to Appropriately Propagate Error. And as I often do, I like to take substantive topics in the field that I work in and use them as sneaky ways to expose people who work on these substantive topics to more to deeper kind of philosophical philosophy of science kind of ideas, and that's exactly what this talk is and why I'm delivering it here at this Metascience conference. But I'll also be delivering it at a substantive workshop on this specific topic area in a few weeks' time. But for now, it acts as a nice case study for me to present some of these meta-scientific ideas. So I'm going to go through, for the purposes of this talk, a very brief introduction to the area of total energy expenditure and the different kind of competing models or theories that explain its determination. I'll then talk through some ideas around theory testing, or how we test theories, the importance of the riskiness of these theories, and how we determine whether observations that we make either falsify or corroborate our theories, and to what extent that happens. I'll then talk a bit about the issues with testing theories empirically, namely the fact that everything that we observe has error associated with it. And when it comes to then testing our theories, we have to appropriately think about how that error propagates and adds uncertainty to our estimates used to test those theories. And in particular, I'm going to focus on meta-analytic evaluation of studies that have tested these competing theories, because there's been some excellent recent work that has attempted to kind of do more quantitative evidence synthesis. And I'm going to take that framework that has been presented and build on that, showing how we can kind of properly propagate error. And then I'm going to finish up with a kind of question to pose and think about, which is, which of these models, if any, is actually true. Okay, so quick background to models of total energy expenditure then. There are competing theories of this, but what everyone generally agrees on is that total energy expenditure is essentially a function of resting energy expenditure, activity energy expenditure, and the thermic effect of food. Now, the thermic effect of food is typically kind of fixed at this approximate 10% of total energy expenditure when at energy balance, which essentially implies that that's 10% of the 10% of the energy you consume is required to extract the remaining energy from it. Resting energy expenditure is all of the energy required to maintain your basic kind of bodily functions. So that is your sleeping energy expenditure, arousal when awake, and also kind of temperature-induced differences in energy expenditure. But the key thing, and this is what has instigated a lot of debate about these models, is the impact that activity energy expenditure has. So activity energy expenditure can be broken down into two components. We have kind of physical activity energy expenditure, was typically what we think of in terms of the energy required to engage in structured or planned physical activity like exercise interventions. And then something called NEPA, or non-exercise physical activity, and the energy expenditure associated with that, which are the kind of unstructured incidental tasks of daily living, fidgeting, play, standing, holding your posture, mastication, self-care, etc. So we have these two competing models, the additive and the constrained model. And as I say, both agree that total energy expenditure is essentially a function of these three things. But the key argument between proponents of these two different theories is what the functional form f actually takes. Now, the additive model assumes that the function is essentially additive as it assumes. So, for example, in the context of changing activity energy expenditure, it assumes that essentially changes to activity energy expenditure contribute proportionally to changes in total energy expenditure. So an increase would produce in activity would produce a proportional increase in total energy expenditure, whereas the constrained model assumes that there is some kind of compensatory function where increases in activity energy expenditure contribute non-linearly to the changes in total energy expenditure. Now, I'll give you a quick visualization of this, and this is the typical kind of figure that you will see in review articles debating these two. So as you can see, in the additive model, we've got these three components: resting energy expenditure, thermic effect of food, and activity energy expenditure. And as activity energy expenditure on the x-axis increases, we see this proportional increase, this additive increase in total energy expenditure. Whereas in the constrained model, and this is only one possible way of framing this, this isn't necessarily to say that this is the specific function, but essentially there are adaptations in other components of the function with increases in activity energy expenditure, such that the total increase or the increase in total energy expenditure is not directly proportional to the changes in activity energy expenditure. Okay, so in terms of the origins of these, the additive model was essentially this kind of pragmatic solution to the problem of trying to determine energy requirements. So, food requirements, and particularly for organisations that provide aid worldwide, or governments that are providing nutritional recommendations, where it's fairly easy to get estimates or predictions of someone's resting energy expenditure. But if we don't know but we can't measure total energy expenditure very easily directly, and so instead, what typically happens is studies look at the kind of ratio, this so-called physical activity level, look at the ratios of, and express this as essentially the ratio of total energy expenditure to resting energy expenditure, which has this direct relationship with our activity energy expenditure. And so essentially total energy expenditure becomes this resting energy expenditure multiplied by some factor, which is essentially derived from our activity energy expenditure levels. And these are done on kind of population levels to provide these energy requirements in order to meet our total energy requirements. And it assumes this additive function, that each of these things independently and additively combine together to produce our total energy expenditure. Now, the constrained model, contrastingly, this was kind of developed from anthropological research that has looked at kind of typical subsistent cultures, for example, like the Hadza, and developed by Herman Poncer and colleagues, where in these populations, despite very high levels of physical activity energy expenditure, their total energy expenditure did not seem to be much higher than in sedentary populations. Now, there's a lot of debate around this and how these studies have been interpreted, but this is the kind of origin of how the model has been developed. But further, there are studies which have experimentally manipulated activity energy expenditure using exercise interventions, and it seems that in some of these, the proponents of the constrained model will argue that you don't see the expected change in observed total energy expenditure based on the changes experimentally in activity energy expenditure. So, essentially, these two models entail different propositions. So, for example, the additive model deductively entails, because of its additive and independent structure, that a change in total energy expenditure will be proportional to the change in activity energy expenditure. So, for example, if we were to plot that, the intercept should be essentially 0 and the slope between the two would be 1. Whereas, contrastingly, the constrained model deductively entails that the total energy expenditure change will be less than the total energy, the activity energy expenditure change. So essentially, despite a similar intercept where there's no change in physical activity energy expenditure, it would deductively entail that the slope should be less than 1 between these two. Okay, that's the quick background. Now we're going to get on to the good stuff. So, first of all, when we talk about theory testing and taking these two competing theories and thinking about them, we need to think about concepts of riskiness and corroboration. And I want to quickly clarify some terminology here. So, and people might use these terms differently, but this is just so you know what I'm talking about. So, when I talk about a theory, which can be instantiated as a model, as the terminology is used here, but essentially this is some substantive causal explanation for how the units in some bounded system, so we've got to have boundaries on, what part of the world we're trying to describe, and at a given level of explanation, interact with one another, and which can be operationalized as a model, as I said. Now, the propositions entailed by the theory are essentially just truth statements about that theory that follow the propositional deductive forms of syllogistic logic. So they are essentially saying, like, if this theory were true, then it logically implies or entails that these this should occur. And these are just true statements. These are just logical statements. There's nothing empirical here yet. But that is where hypotheses come in. So hypotheses are essentially the operationalized forms of a theory's proposition. So these are the predictions that we make about observables. This is where the theory meets reality. And essentially, they're the predictions that the theory entails about the values its units might take when we use empirical indicators as operations to observe those units. So it's when we get out into the world and we think we're going to measure this thing of interest that the theory talks about in a particular way. So our hypotheses are these kind of observable predictions. Now, classic Popper essentially argues that scientific theory testing operates through this implicative syllogism of modus tollens. So essentially, we have two premises. We have some theory that implies some proposition. So if the theory, then some proposition. We have another premise, which would be that we don't observe, or this proposition is not true, and therefore we can validly conclude that the theory is not true. So essentially, if our scientific theory were true, then this proposition would be entailed. That proposition doesn't occur, and therefore the theory is not true. But as I say, what we do is we actually turn this into observational predicates so that we can actually empirically test this. So this is essentially where we turn our proposition into something observational, something empirical, a hypothesis, and allows us to test our theory. Now, there are some additional bits here. It's not just the theory that gets tested, because there are always auxiliaries and other bits and bobs that go into the conjunct of what gets tested empirically. But the logical structure remains the same. It's just that there are arguments and defences that can be put in place in the face of falsifiers. But essentially what we do is we turn that proposition into some materially conditional observable. So we have observable 1 entails observable 2. And this could be, for example, that O1 is the experimental conditions we set up. The theory implies that if we set up this experimental condition, we should observe this as the outcome. And so we can apply this by saying, well, if we set up that experimental condition and we don't observe that outcome, then we can reject our theory. So in plain language, this is like saying, if my scientific theory is a true description of the world, then under some set of conditions, we will observe a particular empirical observation. We don't observe that particular empirical observation under some set of conditions, and therefore my scientific theory was not a true description of the world in its simplest terms. Now, Theories differ in terms of how strong they are based on what the precision of the deductions they entail actually are. So, for example, theories can make differing entail different hypotheses with differing degrees of precision. So, a very weak theory might just entail that there is some effect in a particular direction. So, there is a positive effect, or there is a negative effect for the thing that we care about, or it might make it might narrow that down a little bit to cover some particular range of possible observable values, and the narrower and narrower we can get that up to the point where we can make point predictions, the stronger the theory actually is. A theory may also entail particular functional forms, like the theories that we're talking about with regards to energy expenditure here. But the strength of a theory isn't just determined by, or the strength of a test of a theory is not just determined by the precision of the deductions that it makes. It's also dependent upon the probability that we would observe those things being very small if we didn't have the theory. So what this means is essentially we need to think about what's the background possible range of values that we would observe in these things that we're interested in that the theory talks about. Where it would be incredibly surprising to observe exactly the things that we did if the theory weren't true. And so Meehl introduced this idea of the Spielraum to denote this. So essentially this is the kind of background, or it's a German word that kind of translates as action play or field or range or elbow room, that denotes the range of possibilities given background knowledge alone. So if we didn't have the theory, then what would we expect could be the possible range of observables that we see. And so Meehl kind of clarified this by giving the examples of, as I say, strong theory, weak theory, and an even weaker theory that makes only directional predictions. And he even came up with this idea of an index to consider the degree of corroboration, because even in cases where we have a strong theory, where we have a very wide range of Spielraum, so we might have a very wide range of possible values the things that the theory talks about could take on, and the theory makes a very precise prediction that only covers a narrow range of that, we find that even in cases where the theory obviously hits, we consider that to be corroboration, but a near miss could be considered to be stronger corroboration of that particular theory than in the instance where we have a weaker theory that makes a near miss, because just purely considering the logical space of possibilities, there was much more, there was a greater probability that the theory would, or that we would observe those things just by chance, because they take up a greater portion of the possible space of possibilities. So we need to take into account these various things when we're considering testing theories. We need to consider how precise the predictions it makes are, but precision is always relative to something, and that relative nature is with regards to the background range of possibilities that we would assume we could observe if we didn't have the theory. Now, this is where we then get onto the other problem, which is this problem of observables and error propagation. So, if we think back to what we've just gone through, so a theory entails some proposition, we operationalize that as some kind of hypothesis where we might set up some experimental set of conditions, for example, and that will entail some particular kind of some other observation. So, for example, our theory that is that total energy expenditure is a function of these three components entails that if we set up some conditions where we change activity energy expenditure, we will see some change in total energy expenditure. Now, the function under the additive model essentially says that the change in activity energy expenditure will entail a change in total energy expenditure that is proportional to the change in activity energy expenditure, whereas, as we've said, the function implied by the constrained model implies that the change in total energy expenditure will be less than the change in activity energy expenditure. Now, obviously, what we do is we typically set up, for example, an experimental study where we change activity energy expenditure and we observe total energy expenditure and we see whether or not there is a change. And we're used to thinking about the fact that there is obviously error on our observed outcome variables, for example, total energy expenditure here. Now, in this case, I'm going to set aside systematic error and just assume that's zero, but there's always some random measurement error that's associated associated with it. But in this case, it's not just the total energy expenditure that is observed with error. Even when we experimentally manipulate activity energy expenditure, there's always going to be some error associated with it. So this causes a problem, because going back to this idea of testing, for example, the slope between the two as a test of the propositions, the differential propositions entailed by the theories, we now have the problem of some statistical artifacts that can start to impact the severity of the test that we conduct. So in this case, for example, we have a problem called regression dilution, where if we were, for example, to be able to fit our model to the true values of the things that we're looking at without error, we might, and in this case I've simulated this so that the data is produced by an additive model. Then that we would be able to estimate, obviously with some degree of precision, but we would get an unbiased estimate of what the actual slope between those two actually is. And even in the face of error on our outcome variable, we can get an unbiased estimate of what the slope is. But once you start to include error on the predictor variables, what this does is it has the statistical impact of drawing the slope downwards and the intercept upwards. And so this statistical artifact in this specific example, because of the fact that we have error on both of our sets of observations that the theory would entail and therefore acts as a test, we could end up rejecting the additive model, for example, in favour of the constrained model purely as part of a statistical artifact. Now, in their recent work, Ponser and Trexler have attempted to try and address some of these concerns, and they've developed this interesting quantitative framework for, instead of just directly working with estimates of activity energy expenditure, they take the assumed additive model and then calculate the total expected change in total energy expenditure, which takes into account the fact that obviously, for example, energy exercise interventions can impact other components, for example, elements of body composition that may also have an impact on change in resting energy expenditure. So this is essentially accounting for those things to see whether over and above them the change in energy expenditure that we observe differs from the change in energy expenditure that we calculate as being expected. And they use this essentially this equation, change in activity energy expenditure plus change in total thermic effect of food plus change in the resting energy expenditure expected, tells us what the additive model would assume we should observe. And again, we then go back to this point where we can test this using a statistical model and look to see whether the intercept is approximately 0 and whether we can reject a slope of 1 in favour of a slope that is less than 1. Now, we hit another problem here, though, and this is where all of the components of this are still estimated with error. So, for example, and I won't go through these in detail, you can read their work, but all of these components that are used to calculate, for example, change in activity energy expenditure, changes in resting energy expenditure, changes in thermic effect of food, are all estimated, and all of them are estimated with error, and all of this error propagates then to the change in total energy expenditure expected. So this then means that what we're doing is we are essentially regressing an observable with error on another observable with error, and so we have this potential that any test of our theory could just end up giving the additive model a bloody nose, for example, through a statistical artifact. So we'll now move on to the recent work that has tried to use this framework. Ponser and Trexler have tried to use this framework and applied it from a meta-analytic perspective by essentially synthesizing these studies. So they've taken studies that have manipulated activity energy expenditure, they've used this quantitative framework to calculate it, and then essentially regress the two on the other. But as I said, this expected change in total energy expenditure is estimated with error, and this is an issue because in their current analysis, whilst this kind of quantitative framework is an interesting move forwards to try and determine the expected change in total energy expenditure, their results could be merely due to a statistical artifact. So they estimate the slope to be 0.65 and they reject the 0.01 alpha level, a slope of 1. But like I say, all of this error, even in the meta-analytic context, propagates upwards. So you have the observational, the measurement error level, you have then the synthesis of these into study-level estimates with sampling error, and then each of these components propagates up towards the meta-analytic level, and so we've got this error at every stage that we need to take into account. So what I've done is I've gone back through these studies, and I've also added some additional studies that I could identify as well, and tried to calculate these or try and extract all the information possible that would allow us to propagate all of these errors. Now, what I've also done is be very conservative and assume these errors are independent, which they assuredly are not. And in fact, this probably, what this does is it actually artificially, or it deflates or increases the precision of our estimates more so than they actually would be if we did have, for example, all of these correlations between all of the values, which we don't. So what I've done is I've then fit essentially a measurement error meta-regression model where the error unobserved is obviously taken into account in the distribution of the outcome variable, but also this total energy expenditure change that is expected is modelled as something with error as well, based on the propagated sampling error from all of the components that go into it. So I fit this model. Essentially, it's just a meta-regression model with one predictor variable. We include random intercepts for study in R, as you would do for this kind of multi-level meta-regression. And then what I've also done is I've also added back in the control arms, so that helps with estimation of the intercept, where we know that at least experimentally the change in activity energy expenditure should be 0. As I said, I've added additional studies where I've been able to have sufficient information to propagate them. And then the last thing I've done is I've actually also broken down, where possible, studies that report separately physical activity and non-exercise physical activity energy expenditure, so that we can also see to what extent we can propagate or the EVA model holds up underneath those. Lastly, what I've done is essentially to test the hypothesis of this, I have fit a model which has a fixed intercept value of 0 and a fixed slope value of 1, which is essentially saying an additive model with only the random study and arm intercepts, and then also fit the model obviously where this varies based on total energy expenditure change expected, and then calculated a Bayes factor for these to see under which model is the evidence greater for having produced the data that we observe across the studies included. And this has been calculated essentially such that a positive value for the Bayes factor indicates evidence in favour of the null model, which in this case is the additive model. Now, I appreciate I'm going over time already here, so this is going to be a struggle tomorrow, I appreciate, but we'll see how far we get. We've got one kind of section. So let's take a quick look at the results here. So as you can see, on the left-hand side, we've got the approach that Ponser and Traxler used, and on the right-hand side, we've got that approach, but where I've also broken down the estimates of physical activity and non-exercise physical activity energy expenditure in the calculation of expected change. And what you can see is, I should note as well, these extreme values you see on the X and Y axis are actually from the Race Across the USA study, because they do actually report sufficient data to be able to include them. So that increases the range of the data to test the model as well, which is quite nice. But what you see is it's far less clear that we can easily reject the additive model. Now, admittedly, the slope is less than 1, and the 95% quantile intervals of the posterior distribution on the model, not including estimates of non-exercise physical activity, just about exclude a value of 1. So we might, on the face of it, reject that. But the considering the Bayes factors, there's still incredibly strong evidence in favour of the additive model as being the more parsimonious and better evidence model to have explained this data, which essentially implies that most of the variance that we see is better explained by merely just studying arm level random variance. But also, when we include non-exercise physical activity, it is indeed far less clear that there is any constraint happening in other components that are not just behavioural. So it may be that the lower slope that we see, the slope less than 1 that we see in the left-hand plot, is because of behavioural adjustments. So also expanding it like this allows us to try and tease out which components of our function might be influencing the slope that we see. Okay, so neither of these, at least from my perspective, give me a whole lot of confidence in rejecting the additive model over the constrained model. But that still leads us to the question of which model is true in light of this data. So going back to Meehl's kind of corroboration index, we can think about it in this context, because as I said, the additive model makes very, very risky predictions. It's got a very, very narrow range, and here I've kind of set that as a very small band around a slope value of 1, which is our x-axis here. At the top two facets, you've got the with and without NEPA for the additive model, and the grey band is essentially its model prediction. And I've set the Spielraum essentially to say, like, well, it seems reasonable with background knowledge, and this can be adjusted, of course, but this kind of sets it such that at the very least the constrained model has a 50-50 chance just based on the Spielraum of being rejected or not. But what we find is that the estimates that we have here, because of how risky the additive model actually is and how close the estimates actually are to the predictions that it makes relative to the background Spielraum, we actually get more corroboration, more money in the bank, as Meehl would say, for the additive model versus the constrained model. And because the constrained model, we could end up seeing these observations just purely based on chance, given the Spielraum that we've set. Now, we also have the problem that the constrained model is very weak in the sense that it doesn't specify what the functional form is. So we also have this issue where the additive model specifies exactly what that function actually is, whereas the constrained model could be any number of a possible, infinite set of functions that would produce a slope of 1. And so it makes it a lot more easy to find predictions that are in line with the constrained model, which means that it doesn't necessarily gain as much kind of corroboration as the additive model does by a near miss, even if the constrained model makes predictions that do fit within the range of what it predicts. Okay, now to finish up then, the last thing I want to say is, look, neither of these models are right, even though the data that we've got so far actually provides greater corroboration for the additive model. Omniscient Jones knows that both of these models are wrong, or all models that we create are wrong, and in fact it's perfectly likely that the additive model is, despite having greater corroboration, it's almost certainly wrong, it's almost certainly too simple, and in fact it's even possible that actually over the observed range of data that we have, we have some nonlinear compensatory function that is actually producing essentially linearity over this range of observations that matter. And so, for example, other evidence that suggests there are obviously maximum sustainable total energy expenditures would imply that at some range, above some value of increases in activity energy expenditure, we should start to see this plateauing out. But this is the problem, I think with all of this, is the additive model sticks its neck out a lot more, and it makes itself a lot easier to falsify. But at the moment, the falsifications that we have are not particularly strong, especially when we take into account the error that's associated with them and the uncertainty that's associated with them. But added to that, we also have to take into account that at the moment, the compensatory model, the constrained model, is not yet specified sufficiently to really turn it into a strong theory, because it makes such wide predictions about what we should see relative to background information. So all of these things, I think, need to be taken into account. So to finish up and conclude, as I say, that the strength of a theory and then the severity of a test conducted of that theory really does depend on how risky the theory is in terms of its predictions, and also the quality and uncertainty of the observations made to evaluate those predictions. And the riskiness of a theory can only be considered in light of what we would expect to see if the theory weren't, like if we had no theory, like what is the possible range? Because how precise or how strong or how risky it is a relative term. What narrow range of the possible values does the theory predict we should see under a certain set of conditions? But as I say, we've got to test theories empirically, and we've got to then take into account properly the kinds of error that can go into those, the observational error that we see, and then the error that should be propagated as we start to synthesize things up into, for example, study level estimates that we can then combine into meta-analytic estimates. So we can use these kinds of aggregating evidence synthesis tools for testing theories, but we still need to make sure that we're propagating the error properly for them. And I think what this total energy expenditure debate illustrates is that the key scientific question is not necessarily which model is true in this sense, because in this case, one, the additive model almost certainly is true, and two, the constrained model is not specified sufficiently to say one way or the other, except in some broad kind of vague qualitative sense. But what we want to know is which model remains best corroborated after we have tested it severely, whilst taking into account all of the observational uncertainty and other plausible explanations that we have. Okay, that I appreciate was probably about 10 minutes over what it should have been, and I was already talking quite quickly. So we'll see how we get on tomorrow, and if need be, I might eat into the time because I've not got time to cut this down much. Or it might be that I just skim over some things in a little less detail and allow people to come back and watch this video in their own time. But yeah, this unfortunately, I didn't have sufficient time to get this all prepared and run through and check timings and stuff due to some technical issues with Dropbox syncing and GitHub syncing and working remotely and on my desktop, losing some bits and bobs. So I've got excuses for that, or at least reasons. But anyway, that's the presentation. It will be interesting to see what the Metascience crowd thinks about this tomorrow. We've already had some interesting discussions with people around this notion of kind of what I think is the important requirement for defining this spiel round, whether that is with regards to the theories that are already at the state that they can make specific predictions or quantitative predictions, whether they're narrow range, wide range, or directional only predictions. But also there is the component of thinking like does the theory even specify what the functional form should look like, and what and how that impacts how strong we consider a theory is, and therefore how risky we think its predictions are, and therefore how severe a test of that theory can be. So it'll be interesting to see that, but it will be really interesting from my perspective as well to see how the substantive crowd that work on this area of energy expenditure control think about the importance of these things, given that I would probably wager that most have not thought about this in this kind of way or this kind of detail. So yeah, that's it. Thank you very much for listening.